All right, we're going to continue where we left off with the last lesson. We were looking at the definite integral. So now we're going to start looking at applications of integrals and what the definite integral and regular integrals can help us figure out. So yesterday we looked at one. Let's just do a simple question. So if I gave you the integral of x squared from, say, 0 to 2, so what we did yesterday is we did the integral of that, so that would be 1/3 x cubed, and then we'd plug in the 0 and the 2 and subtract those two answers. So we'd plug in the 2 first, so we'd have 1/3 times 2 cubed, and then we'd subtract 1/3 times 0 cubed. So in this case that would give us 8/3, take away 0. So in this case our final definite integral answer is 8/3. So today what we're going to do is figure out what does that 8/3 actually mean. So from a graphing perspective, if we actually look at this quadratic graph and we look at it from 0 to 2, this 8/3 is actually telling us the area under that curve from 0 to 2. So we've calculated that entire area. So from a physics perspective, remember we did derivatives of distance gave us velocity, derivative of velocity gave us acceleration. So we're going to learn in the next lesson, but we'll talk about it briefly now, that working backwards, the integral of acceleration would give you velocity, integral of velocity gives you distance, and from a graphing perspective, you might remember in Physics 20, if you had a velocity time graph, the distance or the displacement was the area under the curve. So if that's the case, that means the integral of velocity would give us distance, so that means integrals are basically giving us area under the curve. So that's kind of what we're going to be looking at today. So this first example, we actually did this question in the previous lesson, but we'll look at it again. So this is just a sine x graph, so we know it's just a regular kind of sine curve, something like that. It would have 0, pi, and 2 pi, and it would continue, but we're only looking at pi to 2 pi. So from a integral perspective, we would do the integral of sine is negative cosine, and we're going to go from pi to 2 pi. So yesterday when we plugged those in, we went negative cosine of 2 pi, take away negative cosine of pi. The double negatives in the middle, we might as well change to positive. And now if we plug it in, cosine of 2 pi is 1, so we get -1, and cosine of pi is also -1. -1 plus -1 is 2. So our definite integral answer is -2. So what that means on our graph is we've actually calculated this area, and the negative is just indicating that it's below the x-axis. Area is a scalar, we don't usually call it positive or negative, so the only thing we got to do differently is when we're dealing with areas, we need to take the absolute value of any negative section. So for this question, if I changed the question and I said calculate it from 0 to pi, we'd now be calculating this upper area, and that one will give us 2 as well, right, because it's the same shape, but it's positive, so that one would be okay. If we calculated it from 0 to 2 pi, and we did the definite integral, it would actually give us 0, because it's going to take the 2 positive one, it's going to count this bottom one as -2, and it would add the 2 together, which would give us 0. So if we were to actually do this question, the entire question from 0 to 2 pi, and we wanted the area, we actually need to break this apart into two pieces. We would do 0 to pi of sine x, and then we'd add on the absolute value of pi to 2 pi like we did earlier of sine x as well. So the only sort of extra step when we're dealing with areas is we have to take care of the negative values. So this first one would give us the 2, the second one would give us -2, but because we do absolute values, then together that would give us an answer of 4 if we did the entire graph. So that's where we're going with this today. So a couple of key notes, we'll just kind of summarize what we just kind of went through. So the definite integral doesn't mean it is area, but it can be used to find the area. We have to be careful of positive and negatives, but it'll definitely help us solve for area under the curve. And when we say area under the curve, it's not really the best English. when we talk about area under, we usually think below, but it's really the area between the curve and the x-axis. So that question that we just had where it was like a negative, it's the area between the curve and the x-axis. It's always to the x-axis. And then we basically want to make sure we sketch the graph first, and you can use your calculator, just graph it on your calculator. Determine if there's any parts that are above or below. If there are any negative areas, we got to do those ones separately and do the absolute values. And that's basically it for how to calculate area under the curve. So let's look at a different example. So this one, our function is y equals x minus 2. So this graph shows the straight line. And the question is saying, calculate the area between that, the x-axis, from 0 to 4. Okay, so you can see we're using 0 and we're using 4 as our two endpoints. So in this case, when we look at the graph, we can see section A is down below, it's a negative area, section B is a positive area. So that means we're going to have to break this into two pieces. We're going to do the integral from 0 to 2, and that'll be the negative one. So we're going to do absolute values on that one. And then we're going to do the integral from 2 to 4. That'll give us the two pieces, add them together. That should be our total possible area. So we'll break it apart. Here's the first one. So this was, let me kind of resketch the graph again. So this first one is our 0 to 2, so that's showing the negative one. That's why the typing here has the absolute values. So I've done the integral. Integral of x is 1/2 x squared. Integral of 2 is 2x. Now we need to plug in the 2. And we're going to subtract the 0. Do those two calculations separately. That's why I put them in brackets. And then we're also going to do the absolute values of all of that. So the first one gives us 2 take away 4. The second one gives us 0 take away 0. And if we simplify that, we just get absolute value of -2, which would simplify to +2. So the area of that bottom piece is going to be +2. So now we want to do the second section. So we got this bottom one was 2. Now what we're looking for is what's the area of the top section. So we do the exact same thing over again, except we're doing from 1/3, oops, our integral was 1/2 x squared. Let me erase that. So we're going to go 1/2 x squared minus 2x, and we're going to go from 2 to 4 this time. So do the same thing, plug in a 4, and then subtract the 0. So the 0 in this case makes everything, oh, sorry, it wasn't 0, it was 2. I screwed that up again. Let's fix that. So make those 2's. We don't need to worry about absolute values this time because it should be positive, but let's see if the math works out. So let's solve it. We got 4 squared is 16 divided by 2 would give us 8. And that one's also 8, so we get 0 for the first part. Second part, we're getting 2 take away 4, so we're getting -2. So we have 0 take away -2, which ends up being +2 as well. So that means both of these triangles, and they did look symmetrical, so that makes sense that they're both 2 each. So therefore our total area for this triangular shaped piece was 4. So here's another example. We have an equation y equals x cubed. So there's our little S-curve shape. It's asking for the area from -2 to 2. It's kind of blurry, but we're looking at from -2 to 2. So you can see the yellow highlighted area is the piece we're looking for. Again, we've got a negative section, so we need to break this apart. So we're going to do the integral of x cubed from -2 to 0. And that one will be negative, so we'll put absolute values on it. And then we're going to add the integral of x cubed from 0 to 2. And that's it. So we do those quick calculations. We should get 1/4 x to the 4th from -2 to 0. And then we're going to add on 1/4 x to the 4th from 0 to 2. So if we plug in 0, we get 0, take away, plug in a 2, that gives us -2 squared is 16. 16 is 4. This one we're going to absolute value, so we will get positive 4. The second one we get, plug in a 2, we get 4. Plug in a 0, we get 0. So we get 4 plus 4. So again, these are both symmetrical pieces. This one's 4, that one's 4. Add the two together, total area will be 8. Okay, so area is a pretty easy thing. We just do our definite integral. If you have a negative section, separate that piece apart and make sure you do the absolute value to make sure that's a positive value. Add all your pieces up and we're done. So our last thing we're going to look at today is what happens if we have more than one graph. So we can do area between a graph and the x-axis, but sometimes it might be better to do area between two curves. So let me just draw a sketch here. So let's suppose I gave you a quadratic equation like y equals x squared. It would look something like that. And let's suppose I gave you y equals x. It would look something like that. And we can see there's a tiny little bit of overlap between those two curves. So my question is, could we solve for that little sliver of area but that's sandwiched in between those two curves? So it works kind of the same as what we just did. We just got to be careful of a couple of things. You still want to make sure if you have positive or negative values, that's going to still be important. We're going to figure out, once we look at the sketch, whether there's positive or negatives and which part we're actually looking for. And the only other part is, often with these questions, you will not be given the interval. So we're going to have to figure out between what x values does that occur. So for this first one, if I took the equations and made them equal to each other, and we solve it, so let's rearrange it as x squared minus x, and if we factor out an x, we can see that our solutions are 0 and 1. So you can do it algebraically like I just did, or you could even just graph it and use your calculator to help you find those intersection points. But the important point is we need to see what that interval is. So for this graph, we'd be calculating the area between 0 and 1. So that's sort of the second important step. Now the third thing is we're ready to write our integrals. So if you look at the way I sketched this graph, we want the area underneath the blue line. So if I gave you the integral of y equals x from 0 to 1, that would give us the area of this whole triangle piece I'm drawing right now, right? It'd be everything below that blue line. Well, that's good, but we don't want the bottom section, so we need to get rid of this bottom part, which would be the area underneath the quadratic. So we basically just have to do two separate definite integrals. Calculate the total triangle part, get rid of the red part below the quadratic, and the difference between those should be the yellow part that we want. And that's it. So that would be our solution for this one. We can do it quickly if you want. So our integral for the first one would be 1/2 x squared. We're going to go from 0 to 1, and then we're going to subtract 1/3 x cubed from 0 to 1. If we plug in a 1, we get a half. Plug in a 0, it's 0. For the second one, plug in a 1, we get a third. 0 would be 0. The difference between those would be 1/6. So you can see it is a pretty small little sliver area that would be between x and x squared. So the only issue is figure out those intersection points, calculate the area as one graph subtracting the other graph. If you did them in the wrong order, if I would switch these x and x squareds around, we would still get 1/6, but it'd be negative 1/6. And again, the area is positive, so it really doesn't matter what order you put them in. But if you do the top one minus the bottom one, it'll give you the correct value. All right, so let's try another one. So this next example, you can see we have y equals x squared is our top quadratic, and then we have y equals 2x minus x, so we're looking for the area the area in between the two, which would be this little egg shape. So we can, again, need to figure out where those intersection points are. So we need those two coordinates. So we can do the algebra again, or use your calculator, whichever. So if we make these two equations equal to each other, let's bring the x squared over. Let's bring the 2x over, just so get it to look like a quadratic. So if we factor this, we can see we have 0 and 1 again. So we have the two same key points. So we're doing the integrals between 0 and 1. And we can do the integral of the top graph, which in this case is the upside down one. So that'll give us this whole area. And then again, we're going to subtract this bottom piece that we don't want. So the whole area would be the integral of the 2x minus x squared graph from 0 to 1. And then we're going to subtract the x squared graph from 0 to 1. So you could write it as two separate integrals, just like that, would totally work. But because they're the same intervals, they're both going from 0 to 1, we can actually merge these together and just subtract the two equations. And we can even save a step by going one step further. We can actually combine the x squareds to make it minus 2x squared. So you can always do the algebra to make it a little bit simpler if you want. Otherwise, you can do the way I did it up here in blue, would totally work as well. It really doesn't matter. So now we're good to go. So our integral should be x squared. This other one would be 2/3 x cubed. And we're going to go between 0 and 1. So we should be good to plug those in. So if we plug a 1 in, we get 1 minus 2/3. Take away 0 minus 0. 1 minus 2/3 is 1/3. And we can see that is the correct answer for this question. So that's it for that one. So you can see pretty straightforward. Integral of one graph, subtract the integral of the other graph will give you that area in between. Okay, the last question I got is going to be a little bit more challenging. So we've got two graphs again. I've got x plus 1 and then x squared minus 1. That's the upper and the lower ones. So let's algebraically, let's figure out our intersection points once again. So if I make that equal to 0, I would get x squared minus x minus 2. If we factor that, and our solutions would be 2 and 1. So you can see, oops, I screwed that up. It would be plus 1. So we should have 2 and negative 1. So you can see our one x-intercept is at negative 1, and the other one up here is at x of 2. So that looks good based on the way this graph is. This question, though, the way it's given to us, they only want the shaded area between 0 and 2. So we're only looking for the right-hand part, not the negative part. We'll maybe do the negative part afterwards, but let's do it the way this question's drawn. So if we try to do this question like we just did the last one, if we say, let's go from 0 to 2, and we'll take the upper equation, which is x plus 1, and we subtract the lower equation, and whether we do this as two separate integrals or one together, it really doesn't matter. In either case, it's going to give us the wrong answer. And we have to be careful with the logic a little bit when you're dealing with these. So let's look at the areas. So if I do the first part, x plus 1 from 0 to 2, that's going to give us this entire sort of triangular piece. So what I just shaded in yellow, that would be the whole thing. So that's good. So then we need to get rid of the white part. So this part I'm doing in red right now, we need to actually subtract that. So you can see the problem isn't that subtracting it isn't the problem, we just have the wrong domain. We want to do that whole triangle piece, but now we want to subtract the red part, which would be from 1 to 2. Right? So you can see that one only starts at 1 down here. So we need to go from 1 to 2. So that would give us the blue part on the top that we want, but now we can also see we're missing this bottom part. So we actually need to also figure out what is that bottom section. So we're going to have to add on the negative part as an absolute value, and we're going to go from 0 to 1 of just the bottom graph, which would be x squared minus 1. And that'll be absolute values. So you can kind of see, in this case, we just have to sort of break it into three pieces. We need to do the top minus the curve to get this upper part here that we want, and then we got to add on the negative part on the bottom to get our total shape that we're looking for. And that's it. Once we break it into three pieces, it should work just fine. So in this case, our first integral would be 1/2 x squared plus x, and we're going to do that from 0 to 2. The second one would be 1/3 x cubed minus x, and we're going to do that one from 1 to 2. And then the last one is our absolute value of 1/3 x cubed plus x minus x. And we're going to do that one from 0 to 1. So we have one section being subtracted, the other section being added. And that should be it. We should be able to plug those in. So let's do it quickly. Plug the 2 in. We get 4 divided by 2 is 2, plus 2 gives us 4. And that'd be 4 minus 0, so that one is just 4. The second one that we're subtracting, if we plug in 2, we get 8/3 minus 2. And then we're going to subtract 1/3 minus 1. So that gives us 2 would be 6/3, so that's 2/3 minus 2/3, which should be 4/3 if I did that right in my head. So that'd be the area for that red part. And then the last section is our absolute value. Plug in a 1, we get 1/3 minus 1. Plug in a 0, we just get 0. So that one should be negative 2/3, but the absolute value will make it positive 2/3. And that's it. Oops, I messed up my middle one. It was minus, not plus. So that one was 4 minus 4/3 plus 2/3. We put all that together. That would give us an area of 3 1/3. So it works the same. You just got to be careful to make sure you get your correct zones and make sure you add and subtract properly. So let's kind of go back to my original question when we looked at this, is what would happen if this graph was actually the entire thing shaded, not just that above 0. So if we're looking to calculate that whole in between both graphs, in this case we would go from -1 up to 2. So the only thing that would change is our original triangle type shape graph. We would have to go from -1 instead of from 0. Let me change that on here. So this first one would be -1 to 2. That would give us the entire triangle part. We still want to subtract the exact same part that I've got shaded in red right now. So that would be still from 1 to 2. So that one wouldn't change. And then we'd add on the bottom part, but we need this entire bottom instead of just half. So that would also change. Our last one would be from -1 to 1. And other than that, it would be pretty much the exact same. So our numbers would change slightly. This one here, instead of it being a 0, would be, we would have a half minus 1, so this would be -1/2. So that would change that to 4.5. The middle one would stay the same. And our other one, when we plug in a -1, we would get 1/3, -1/3 minus 1, minus 1. So that would give us 2/3. So that would be, we'd get another 2/3 on there. So we'd have 4/3 minus 4/3 would cancel. So in this case, the entire shape would be 4.5 instead of 3 1/3. But that's it. So you can see it works the same. It doesn't really matter by us cutting it into a section or not, but we have to still break it into three different zones. And that's all for today.